So now I want to go to another thing. Let me try to make sure I did not write anything wrong. So I review again. Why? Because I want to talk about another important property of feedback. So we spend a lot of time to talk about 4 types of amplifier: voltage amplifier, transimpedance amplifier, transconductance amplifier, and current amplifier. Okay? And we emphasize the importance of their input and output impedance because they are not ideal, right? They in the real life is not ideal. But by understanding their function, we can help ourselves to memorize what value they should be. For example, a transimpedance amplifier, what is it sensing? It's a sensor for what? For transimpedance. Current. Because the input is current, you try to sense the current. What type of source it is? Is it a voltage or current source for transimpedance? It's a voltage, right? Impedance, right? The V out divided by V in is I in, right? So because I'm current sensor, I want to have a low input impedance. I'm a voltage source, I want to have a low output impedance. So I want R out, R in to be both small. Okay? So if I hook it up in the feedback, what will happen? You see that I just have one slide cover maybe 10 pages in the textbook, and we save a lot of time. Because with feedback, you only, so far I think the only drawback is you have lower gain, maybe larger layout area, more power consumption. Everything is better, including the input and output impedance. It's going to change the input and output impedance in the way that you want. But what is the desirable way? It is the way to make your amplifier more ideal. For example, we just talked about this transimpedance amplifier. It has an R in and R out. So if I tell you that if you hook it up in feedback, it will be a more ideal transimpedance amplifier. Do you think it's going to increase or reduce the R in? Huh? Reduce. Can you explain one more time why reducing it is making it more ideal? Because you want zero, zero, but why do you want zero? Good, all the current. Because the input is current, so you are sensing the current. So the ideal case is zero, right? So you want to reduce it. So you're right. So now without doing any derivation, I know that with feedback, R in is to be smaller. How much smaller? Can someone guess, intellectual guess? You have no chat GPT, but what is the input impedance? Basically, we have learned so far. If you need to guess, how would you guess it? Will it be R in minus R in? Then it becomes perfectly zero. Maybe no, too ideal, right? What else can it be? It is smaller, divided by 2, divided by 3, or what? What did you just say? Huh? He mentioned K. K is a very important stuff, right? Now he said divided by K. K usually smaller than 1. So then you are going to increase it. But you're close. You already find the K. What else determines the feedback circuit? Is it just by K itself? One plus K R 0. So he came back to this magic term. 1 plus Ka 0, right? This is a very good guess. Because your whole system, you reduce the gain by 1 plus Ka. You increase the bandwidth by 1 plus Ka. And what else? Nothing else, right? Did we say anything else about 1 plus Ka? Yeah, nothing else. But maybe the impedance also reduced by 1 plus Ka. And indeed, this is the case. And that's why I asked you to memorize that term, right? So why I spend so much time to do those super basic trivial thing? Because at this stage, you can just modify it so easily. R in becomes R in divided by 1 plus KA. But because this is not A, the gain is R0. So I just put R in divided by 1 plus KR0. Is this okay? Do you understand my logic? Hand waving logic? Yeah. If you don't agree with me, what will you do? Prove it. It's in the textbook. We will prove one of them in this class. Okay. Now, can you tell me what will happen to R outs then if I tell you that it's going to modify in the way I want, make it more ideal? You say increase, why increase? You say decrease, why decrease? Because this is a very good. This is a voltage source. You want it to be 0, right? So there's no voltage drop, like what he said. So if decrease, how will it decrease? Divided by 2 or what? Yeah. I mean, if you no choice, this is the best guess, right? And indeed, this is the answer. I mean, you already have the feed forward. That is what I draw, right? So, but I did not draw the feedback. I just said, what if you put this in a feedback circuit?
Yeah, thinking any signal adder that we could come up with to add a signal back into the original input signal. It would also feed data back because electrical circuits.
You're saying that this will feed through to here. Yeah. You mean talk things
I'm
this
saying
by
that it will feed all. So in the ideal world, it wouldn't feed back through the adder, but I'm saying that it would go through K through X to K to Y as well.
Oh yeah, of course. So then this will not be a, but we will make it so that this is very weak. For example, like transistor, right? It's difficult to feedback from the drain to the gate. Yeah, unless you have super high frequency. Yeah, you're right. Yeah. So this is unidirectional, right? You're just saying that, is it possible I have signal going from here? Yeah, possible. You're right. But in this class we don't. Okay. Okay. So anyway, in that case, how about let's do some exercise. Be more interactive. The first row student, right? Can you tell me, any of you over together, how should this out in be modified? First, what type of amplifier is this? Sorry, I mean first column.
You're not the first column. Come on.
Yeah, first row. Yeah, I'm talking about first column. I just say first row though. The 3 students over there. Thank you, voltage. Okay, so maybe you can tell me directly what should be out in, how should it be modified if I say it becomes more ideal after the feedback? Goes higher infinity. So how will you modify it? If you don't have the cheat sheet and you need to answer. 1 plus K instead of RO because the gain here is A0. Very good. So A0. That's how it's. How about the output? How will you modify? How will it be modified? Become 0. So how will it be modified? 1 plus K is. Thank you very much. Yeah. So basically they say this is voltage amplifier. Recognize that the input is voltage, output is voltage. So it's a voltage sensor. Voltage sensor want to have very large impedance. So that's why R in times 1 plus KA0. This is voltage source, so it's out divided by 1 plus KA0. Okay, great. So we are done with this. How about the second column? This is called row, right? I don't know. Oh, thank you. No, this one. Yeah. Good, good. Transconductance. Trans GM, right? So how would the input impedance be modified? In Thank you. So it is larger, right? So why? Because this is a voltage sensor, right? So you want to have a large input impedance. So desirable ways means make it larger. This is, I'm trying to help you to memorize, right? This is not logic, not because I want it to be larger, then it becomes larger. Remember this. But we can prove that this is true, and it is in the textbook. How about this R out? What will it be changed to? To be infinite because it's a current source. Good. Thank you. 1 plus K GM. Yeah? Okay. Everyone agree? Okay, this third column. What type of amplifier is this? Current amplifier. So how will it be modified? I. Yeah. Because it's sensing the current, right? So you want to reduce the input impedance for an ideal case. And then how about the output? Why is that? So why you want it? Why it should be bigger for ideal case? What is this? The output is what? No. It's current, but its output is a source or sensor. You output something, yeah. So it's a current source. So that's why you want to have a larger output impedance. Okay. Great. This is just help you to memorize. If you cannot memorize, write in cheat sheet. For example, how about in the future when you interview or whatever, right? Then you try to memorize. Let's try to derive, try to prove what I said was correct. Let's look at this voltage amplifier. Voltage feedback, right? So let me draw the circuit again. So we have this feed forward, which is A0. Then I sense it. Then I have this K feedback. This one is going to come here. And this is the V in input. The V in is going to add to this feedback VF. This is plus, this is minus. And then this guy will come here. Let me call it maybe Z. Okay. Now this is the ideal one that we have been working with, right? It's the same. Okay. Now, but we assume it's not ideal now. I have an amplifier. This is the voltage amplifier. Okay. And it has an input impedance. So I model this input impedance as this. R in. Okay. Now, so when you have no feedback, I look into here, I see R in, right? Instead of infinity. If it's ideal, this will be gone, I see infinity, right? The input impedance equal to R in. Okay. Now, what if there's feedback? Then let's find the current. How do you find that? Find the input impedance. What is the definition again? What is the definition of input impedance? Again, be brave to say it.
Put in the voltage, measure the current out.
Would voltage and then
Current.
measure the current, right? This is very important. I mean, very simple, but do not get scared because of so simple, right? That's it, right? Of course, then the V out needs to be open, right? But it's talking about this one open. I'm not connecting to anything, so I fulfill the definition, right? So my goal is to find out what is V in divided by I in this case, right? Now, I can tell you all this I in will go to here. Okay? I will explain later. Trust me, because this one can be confusing to you because isn't that I have something here, then you start thinking about KCL, maybe some I in will come to here. I will show you why soon, right? Just trust me, the I in will all comes to here. So if I in comes to here, what is the value of Z? What's the voltage at Z? Where does this I in go? Go to R in. Yeah, very simple. It's just equal to I in times R in. Okay? Because this is ideal, right? It's just confusing, but we need to but you need to think in this way. Is that okay? Because this is like a block diagram. Any questions? But what is Z in this case? What is Z? How do you get Z in this feedback circuit? V in minus Vf, yes. But what is V in minus Vf? What is Vf? Yeah, this is V out times K. Yeah, V out times K. Very good. What is V out then? C times A naught, but then we will keep looping. Now we use the closed loop gain. Very good, right? It's equal to V in times A naught divided by 1 plus K A naught. Because V out is equal to V in, right? Times the closed loop gain. Okay? So this one means that Z equals to 1 plus KA0, and then I have V in times 1 plus V in times KA0, so these two get cancelled, right? Do you see that? V in times 1, V in times KA0, and this is V in times KA0 negative, so they got cancelled. Okay? So therefore, V in divided by 1 plus KA0 equals to I in divided by R in. So what is R in dash? Is equal to V in divided by I in, right? By definition, which is equals to R in times 1 plus KA0. Right? So now the input impedance is increased by 1 plus KA0 times. Okay. So this is the proof. But here, what did we say? The input impedance is increased by 1 plus KA0, right? If you go through all this math, you will see that they're correct. You can refer to the textbook, right? But we are not going to show this in the class. But I do you need to be able to know, to memorize this, right? Either on cheat sheet or I already go through the reasoning with you. You should be able to do it even without the cheat sheet. Okay? Any questions? So the confusing part is why I can say I in equal all goes to here. And then it comes to the what is the meaning of a comparator, right? To be frank, how do you do a subtraction of the voltage? How do you do voltage subtraction? How do you add up the battery voltage? How do you put them together?
Put them in series.
In series, right? So in the real implementation, this is just a block diagram. We say we're going to subtract this. We need to do something so that they are in series. I put them in series, but look at the sign. This is plus minus, this is minus plus. Then this output is V in minus V2, right? Just now you flip the battery, maybe 9-volt battery with a AA battery. You flip it, then you become 7.5 volt. If you want to get 7.5 volt. So, okay. Now, so if that is the case, then I'm talking about my V in has this current going up, right? Then isn't that they all goes to this part? They are not going to this part, right? I mean, they go to this part, but no change. So this is just a block diagram to indicate that I'm going to do a subtraction of V in minus V. But in an actual implementation, it needs to be in series. Right? We will talk about how to implement, but I hope that this can solve the confusing part that why I can say I in equal to I in here. Right, so similarly, when you do the derivation for other circuit, you need to be careful about this subtraction, how they add the current, how they subtract the current. Any questions? Okay, if no, then we are done with the feed forward. And now we know